So we saw up to now many applications of hydrogen technology, so development of membranes and also complex electrochemical system and electrodes. And now we want to take a step back maybe and give you a bit or discuss together this electronic transition, this new transition that we are trying to develop into a new energy society. And what is the role of hydrogen into this transition? So so this is the outline of my talk. So I will give a little introduction, then hydrogen production, hydrogen use, and then a little future scenario conclusion and perspective. Yeah, so what we are facing now is a great challenge to transform our society. And a key part of this challenge is to replace fossil fuels into new energy source and energy carriers that has to be sustainable, environmentally benign, and affordable. In order to do this, this challenge, we can see that is strongly entangled with other processes, such as the growing population that we are experiencing. So this is a graph from Population Matters, where you can see not only that we reach now 8 billion people on planet Earth, but what is also important is to see how quickly we are rising these numbers. So we are more than double today that we were in 1970. So this is a quick, very quick rise on terms of population. And of course, this big increase in population implies also an impact on the environmental problem that we are facing. When we look at what this increase of population can imply, we can look, for example, at global carbon dioxide emissions by fuels. And you can see here that we have also this very steady rise in the emission of global carbon dioxide. And so that seems to correlate with the increase of population, and also what we see when we can actually look and we can identify like a dip in this graph. For example, we can see here the global financial crisis in 2009, and then here the COVID-19. But what also is interesting here to see is that immediately after the dip, the CO2 emission actually were able to regain their steady rise. And so this is important to show how the impact of CO2 emission from this fossil fuel like gas, oil, and coal. Therefore, and other processes there. So when we look in more detail, so where are these emissions coming from? In this case, it's not CO, but it's global greenhouse gases. And we look at sector, we can see that actually the problem is very complicated. So we have emission from many different sectors. And the energy sector is actually the most impacting, but not the only one. And we can see that it takes it account as 3/4 of the total emissions. And this itself, this energy sector, can be divided into many different types, of which, for example, the transport, the heating, are a big contribution to this emission of greenhouse gases. Therefore, we can see that to achieve actually net zero emission, we need innovation in many different sectors across these human processes. And so one way to actually find a solution, which, as we can see, is not simple because it implies solve many different challenges, is probably to decarbonize, so strongly decarbonize and electrify these processes. But we know that some of the renewable sources, they have intermittent availability. This is the case, for example, of solar and wind, as you see here in this graph here from Germany, a week in 2018, and as we experience every day. And therefore, it's very important that we are able to actually convert this energy and to storage in a way that we have available when we need it, so that we basically, in other words, we are able to decouple the generation and the consumption of this energy. So this is therefore the energy conversion and storage technology will be really a pillar of this energy transition. Okay, so what can we use to store energy? So here is a plot that I took, and you can see that we have basically on the y-axis we have the energy per volume, the so-called energy density, and then we have our volumetric energy density, and on the x-axis we have energy per mass. So in this plot called specific energy, sometimes also referring to as gravimetric energy density. So basically tell us how much energy we can put in a volume of our fuel, or how many energy or our material or device, and how many energy we can put in per mass in our system. So this is, of course, two very important quality. So basically where we want to be up here, right? So we want to put a lot. But of course, for various applications, there could be some more preferential way. And where you can see is that many fossil-based fuel, you can see here in this circle here, fossil-based fuel and petrochemical products has very good energy per volume and also quite good energy per mass. So not surprisingly, they are actually used, and they are very good in this term as energy density storage system. On the other hand, we can see that hydrogen is also very interesting, because as we can see in the bottom here, in the bottom right, it has a very high energy per mass. So this is actually quite important, while it's a bit more critical in the energy per volume. So it's correct to also show what are the pros and cons, but this fact of the energy per mass is actually extremely appealing, and you can see also where it's stand in comparison to lithium-ion battery. So this makes hydrogen, of course, extremely interesting, and another interesting application of hydrogen is to the conversion to derivatives. We saw a great example with the talk of Pau, and so here for example, as Pau showed, it can be combined with carbon dioxide from CO2, or to produce hydrocarbon, and then it can also be used to produce ammonia. So this application as a derivatives also very interesting. Okay, so this brings me to the next part of my talk. So now we saw a little bit like an introduction, like a global perspective, and we identify hydrogen as an interesting candidate, and now we can see how we want to make hydrogen, or what are the possible paths. And as you can see here, this is a wide scheme of the different type of hydrogen that we could have, that is being often referred to as the colors of hydrogen. And if you want to, this is from a very nice review here, or article, but also if you want to know more, we have also a nice post on the ANEMEL website made by Agatha, our partners, where you can also read about these so-called colors of hydrogen and what they imply. So here we see that we have the black and the gray hydrogen here from coal, for example, gasification. And then when we are actually interested to in these talks is to talk about the green hydrogen, so that you find over there. So this is from the green hydrogen obtained from electrolysis by using renewable energy sources. And this is one of the so-called clean hydrogen, and is the one that we are interested in this talk and for this audience, because it uses electrolysis, and that's what I'm going to talk in the next slide. Of course, other sorts of hydrogen are also interesting. For example, the blue hydrogen here, where you actually, the carbon that you emit, you recapture. And I also discussed today as interesting application and pathway towards decarbonization. So we said hydrogen can be produced by electrolysis, by using renewable energy sources. And this is called green hydrogen. And here I just showed to you 4 major types of electrolysis technology. These, of course, are not the only one around. There is more alternative approaches, even membraneless and so on. But here I just focus on the one that are more majorly discussed and developed, and they reach a very high level of TRL and commercialization. And one of these is the alkaline water electrolysis that we also heard before in the talk from Denora, and also in the previous talk from Chile. So you can see, so we have alkaline electrolyte is the furthest to your left. Here, alkaline water electrolysis. So we have the electrode. They are in high concentrated KOH solution, and we have a separator, a diaphragm. And this is very well established with many years of operation. Then we have here the PEM water electrolyzers. Here we have the PEM membrane in the middle. And you can see you can run it with just the water in this case. And the membranes allow the transfer of protons. And this is another commercialized solution with megawatt electrolyzer that one can buy. And it's quite established. This as one... it requires the use of noble metal catalysts, for example, in compared with the alkaline water electrolysis, and they have, of course, many different other properties that I will not go in detail now. And but these are maybe the most, I would say, or two examples of these moderate low temperature approaches that are very well commercialized. Then an emerging solution that we also hear a lot before from Chile is the anion exchange membrane water electrolysis type of electrolyzers, where we use our membrane now allows the transport of OH minus, and here we can use noble metals. And so this is a bit an emerging concept, and we saw before what are the challenging, especially related to the membrane, but also in the stability of material and so on. And finally, I just would like to mention also the high temperature solution. Here I combine in just one type of device. High temperature solution include different approaches like solid oxide, proton ceramic conductive. But basically, this work with water steam, and here the transport is of oxygen and ion. Okay, so this we also review in one of our review in Nature Energy a couple of years ago, the different approaches, and you can hear there more. You can read there more details. Okay, so now I show you some different approaches very quickly, and now we can see what are actually the components of this type of technology. So here, what is important to realize is that it's actually a multi-level system. So if one wants to optimize this technology, has to look at different level of complexity. So we have the system level, where here I show a slide is of course extremely simplified. So, but just to show that what we have is that we have the tank, for example, for the gas, the two gases, and their separator, gas separator. We have dryer, and we have the electrolyzer stack that is, we can say, is maybe the earth of all the plants. And then we have, of course, the renewable energy and all the components for the electricity part. So this is a way of complexity, the system level, but then we can go more inside and we can look at the stack. So in the stack, we see that we have like a component here that is called a cell. So where we have bipolar plate, and then within the cell, we have a membrane, the separator, we have a oxygen evolution electrode and hydrogen evolution electrode. And then we have a porous transport layer here that connect the electrode to the bipolar plate and allow the mass transport in this cell. And then by repeating the cell multiple times, you form this stack. And the development and the optimization of the stack is like a level of complexity on itself that require, is challenging due to the big dimension involved, so the optimization of the parameter and homogeneity and dishomogeneity that can happen in this type of system. Then, of course, as I already have been introduced, we can go even further and go into the cell level. So when we look at the cell, we can look a bit more in detail of what happened in this catalyst layer. And you can see here that in green, you see here is a membrane. And then we can see two types of catalyst layer development here. We have, this is an example that refers to PEM, water electrolysis. So where you can see we have as anode, we have iridium and ionomer inside. And then as cathode side, we have also the ionomer. And then we have platinum nanoparticles on a carbon larger support. So here it shows you like the level of complexity that we can have, because all the component needs to be singularly addressed and then also understood where they work all together in the system. So to understand them separately, we can study them with some sort of ex situ method or method in a 3-electrode cell, where we can singularly address, for example, the catalyst, but then they really has to be understood when they are inside the cell, how they activate, how the system perform. Yeah, and here is an example how we can look into how they work within the cell. Actually, it's very difficult to look inside the cell. So when you mount all this material together, normally, you look just at the voltage that include contribution from all the components. And then what will be very nice is to actually be able to look at the different components singularly. And in this work that was done, it was led by EPFL from the Jan van Erle group, first author with Suaz, and we also collaborated by discussing the protocol and implementing it together. And here they actually were able to develop a setup where you can insert a reference electrode, and then by involving also advanced electrochemical impedance spectroscopy, we were able to actually separate the different components. So you can see here that we have the ohmic contribution. This often is can be extracted by high frequency resistance. But then what is also very important here is that we have the cathode and the anode contribution separately. And this is actually providing you some important insight to understand what is the problem of the cell, or how the different material activate and how they degrade together. So this is like quite an active field in the research. And actually in this specific case, what is interesting is to show that in this condition, where we use actually just a nickel fiber, rainy nickel or nickel fiber as cathode. So the cathode side, actually the loss, so here what you see is actually the cell voltage versus the current. And you see here that the cathode contribution is actually comparable to the anode. And this is, for example, not normally seen for when you have platinum at the cathode, but in this case, it's actually happening, and this provides you, therefore, important insight in the system. So these measurements are done in 1 molar KOH, but then we can see here instead another example also published within ANEMEL. So this work was done by us together with Denora, from Anna and Lisa here, where we basically look at different architectures. So from going to, before we saw different contribution in the cell, now we actually focus on the catalyst layer, and we see how can we change the architecture within the catalyst layer. In this case, we look at the cathode, and you can see here in the pink, we have the catalyst layer where we have just the catalyst on a support, so without any ionomer. And then we have the green, we have the we added the ionomer inside, this orange spaghetti. I would say, yeah, I'm Italian, so that's the first thing I thought when I said. But and then finally in the bottom we see the ionomer top layer, when we add the ionomer between the membrane and the catalyst layer. So in what you see here is actually, when we look in this plot here on your right, you can see that in pH 14, so in 1 molar KOH, you can run actually with reasonable performance with this pink you see here, also without ionomer at the cathode. But when you go to pH 12, you can see how bad the performance become. And actually in adding the ionomer layer really improve here at the lower pH. So by changing operating condition, even within the same type of electrolyzer, the same type of materials, but just changing the configuration of one of your cathode or one of your catalyst layer, you can actually improve the performance really a lot, especially in this very challenging low pH feed. Yeah, and this I wanted to conclude the hydrogen production with a couple of examples, and now we can see we can look briefly to how then we can use this hydrogen that we produce. So there are many applications of green hydrogen, a bit were discussed before, so energy application and feedstock for ammonia, for example, methanol synthesis, but also other industrial process, just as steel production is also an important application for the future, and as well as transport and industrial heating. Here we see for example, the percentage of the global demand of hydrogen through this various process, and we can see also where this hydrogen come from at the moment. So we can see that, of course, electrolysis is only a very small contribution of this at the moment, and we are trying to increase this contribution. Of course, I think it was also mentioned by Chile, the problem, the cost challenge to get cheaper green hydrogen respect to the hydrogen from, for example, steam reforming also. So here is other series of picture to show you some application of the green hydrogen, especially in the industry sector. So steel production, cement, and then other chemical processes and industrial processes, such as for the ammonia we said, and fertilizer, and so on. So this also shows how diversified our use of our hydrogen can be. And here is again like a couple of examples with the processes. So here you see the type, for example, with the green steel. So the steel, which means the steel where we use hydrogen here to produce the steel from the iron oxide instead of the coke. And then we have also the ammonia, of course, the methanol, and so on. So it's really diverse, and it's very interesting. And there are already companies that are applying this, for example, for the green steel. So the industrial application we saw briefly, and now we also can look at transport applications. So where are we standing now? First, let's talk quickly about passengers. So these are so-called light-duty mobility application. And here the technology in use is the fuel cell technology. And actually, you can see here a photo of two cars that you can buy nowadays in Germany. So the Toyota Mirai and the Hyundai Nexo. And so it's interesting to see that, so for someone that work in the field for a lot, to see that you can actually buy this car with fuel cell. And also interesting to see that the even though in Europe and in Germany, but in Europe in general, we have many car manufacturers, actually the market is now dominated by two Asian brands in the field. Even though, of course, all the companies are researching, or many companies are actually researching this. And here is another, of course, so we related to the car is the one problem could be the infrastructure. So this is, of course, for hydrogen is actually quite a challenge to implement a refueling station. But you can see that actually it's something is actually happening in Germany. So you see many stations here. Ljubljana will be here is a bit covered, but I'm not sure if this map is actually taking that data there. But definitely from Germany, we can see we have some station there. It's of course exciting to see, but of course we can see also that we have a long way when we compare to gasoline fuel station and so. And here is the specific case of Berlin. So we have 4 stations operative where one can refuel his car. Okay, so Yeah, so the infrastructure problem for hydrogen refueling is a big challenge, especially for the light-duty vehicle. But things can change a little bit when we look at how many other type of transport are actually we can consider. So one application is the material handling here. This is actually quite interesting because I think the big advantage of this type of application is that this type of vehicle, they don't necessarily have to move a long way. So they are in their factory or logistics center, and they just need to operate all the time. So fast refueling could be interesting. And so it's actually quite an important application where hydrogen can actually have a substantial impact. Then we have the passenger cars, you can see here. So this also show is a plot for how many miles per day this kind of transport vehicle are meant to run. Exactly, so this we already spoke about. Then we have the delivery trucks, so this on the city buses, so-called medium duty vehicle, and then we have the high duty vehicle here, then include trucks, so many transport on long distance, especially in US, but also in Europe, is still relying on this type of transportations. And then we have also trains, ships, and aircraft. And actually what is interesting when we move our focus from light duty to these heavy duty vehicles, we can see that since these are meant to operate on a longer distance, so here operation costs become very important, and therefore also the way you design your system is also, you can tune the parameter in a different way. So your strategy not necessarily is the same as is not necessarily the same as the passenger car. So here you are really to focus on efficiency because that implies the cost, so how many hydrogen you consume. So it's operating cost, yeah, the range, and also refueling time, durability. Durability is really the key here. And yeah, plus on top of this, the interesting here is that, for example, many times, this vehicle has to maybe just go from one point to another point. So in terms of infrastructure, it's much more easy to develop because you can just have your hydrogen refueling station on one end and the other end. And then, yeah, this simplifies. So there is a strong now push, and maybe this will be the first big, or it will be dominant a bit in the field of moving to fuel cell actually in the near future. Okay, so we spoke a little bit about fuel cell, and when we look, this is an example of a PEM fuel cell that is basically what is at the moment dominating as commercial solution in the market. You see that it's very similar actually to what we saw in terms of PEM water electrolysis as a structure. So we have a membrane electrode assembly with the catalyst of both sides. Then we have what is called here GDL, but it's still your transport layer. And then we have the bipolar plate at the end. And yeah, when we look again inside, we can also see that in this case is every component has its own complexity, and the catalyst layer also here is made of, for example, nanoparticle on larger nanoparticle support. So we have different scale of complexity from nanometer to micrometer and so on, and that require research in all these aspects. In this case, also water management is a big challenge, and yeah. So that's what researchers are active nowadays. And here is just a quick example of where are the costs distributed. So for PEM fuel cell stack, this is based on a 160 kilowatt system, and it's basically show how, for example, yeah, a big part of the cost is taken by the bipolar plates because yeah, they are very massive, and yeah, they take a big part of the cost, but also the catalyst and the application, because we are in PEM, we have to use platinum, so we are strongly relying on platinum. So a big, like a great challenge in research is to reduce yeah, the amount of platinum to achieve a certain kilowatt of power. And here just summarize like what could be one of the target to reach. Yeah. yeah, so with this, I will go quickly to my the conclusion with the couple of slides, just the future scenario. So we saw a bit a global overview, then hydrogen production, hydrogen use, possible utilization, and then so what we need to do for the future. So one, actually, like what is peculiar of these systems is there are trade-offs. So there are trade-offs between, for example, efficiency and durability. So you would like to increase the efficiency, but what you try to do, it might impact the durability. And maybe just to make an example, to not use too much time, maybe one of the simple examples would be the membranes. So for example, if I want to make my membrane maybe more durable, I will try to reinforce it, but this will most likely increase the size of your membrane, and this will imply a loss of efficiency in the system due to higher ohmic loss and so. So it's always a compromise that one has to consider, and this is what we have to try to find, so the best solution. And there is in all these developments, so including also, as we saw, the system level and so, electrochemists actually can have a big impact, because as we see here, there is many part of the system that electrochemists can tackle and solve this challenge. Yeah, so here we so again like a breakdown in this case of a PEM electrolyzer, and we can see that the balance of plant is not negligible. It also can take some a big amount of the cost, but also, as we said, our stack and our catalyst part. Yeah. And here, for example, this report here shows what are the impacts. So we know that we can affect many components, and there are some that are expected to have a potential impact for reduction. For example, the bipolar plates and the catalyst, and the higher potential for cost reduction, the power supply and this part, while the stack assembly part is considered that it cannot be optimized too much at this point of the research. So this gives like just an overview of where we have to go. And here is also a final overview of this is at the point in 2020 of this report. This was the cost of hydrogen in dollars per kilogram. And we can see what we can do to achieve the goal in 2050. So having, in this case, was very ambitious $1 per kilogram of hydrogen. And basically what we can see is that, with the electrolyzer system, if we are able to decrease so much, this will be what we need to do, so an 80% of reduction in electrolyzer cost. But also it will be not enough, so what is expected that has also to be reduced is the electricity cost. So that's actually another big factor in this future scenario prediction. And so this brings me to the conclusion of the talk. So we saw that green hydrogen can play an essential role in the energy transition. It acts as a green energy carrier for the transport section. It can help decarbonizing many industrial processes, such as steel, ammonia production, methanol. And it works as electrical energy storage, and it can provide heat for industrial heating application. And therefore, what we can do to reach this, to make this actually reality, so we have to actually make electrolyzers and fuel cell cheaper, and at the same time, we also need the electricity cheaper. So this concludes my talk. And I would like to acknowledge Professor Peter Strasser, with which I worked for many years, and also gave me some of these slides, so thanks. And also the 4 project where I work, so ANEMEL, that is also well represented here with this poster. Then Asterisk, where we try, so in ANEMEL is an ion exchange membrane project where we look into impurity and the effect of the impurity in the system. Asterisk, we look at the big challenge of seawater electrolysis. And then we have, I also work in Duralist, where it's also an ion exchange membrane, but is on strongly focused on durability. And then I work also in Highlander, that is about a heavy-duty vehicle fuel cell application. And I also like to thank all the partners that are working in this project, that some are here, and some are at home, and are maybe will follow the talk. And also thanks to you to be here. And yeah, I will be happy to answer questions in the follow-up question session.